In this video we're going to go over how to draw Morse circle. So in the last video we talked about calculating principal stresses and max in-plane shears, and we did it all with equations, which is just fine. Morse circle is a great way to visualize how to calculate the principal stresses and how to calculate really any stress transformation, and you can do it all with this visual aid of Morse circle. Don't even have to memorize any equations really. So it's a very convenient way to do stress transformations. So let's just start by drawing Morse circle for a general stress element here. So we have our normal stresses. This is in plane stress again. We have normal stresses of sigma x and sigma y, shear stress of tau x y. All of these stresses right now are drawn in the positive notation according to our sign convention. So to create Morse circle, we first start by creating axes. So in Morse circle, something important that we need to specify, we're going to specify that this axis here is going to be the normal stress axis, and it's positive to the right. The vertical axis is the shear stress axis, and it's positive downward. Okay, so normal stress axis is the horizontal axis, positive to the right. Shear stress axis is the vertical axis, positive downward. So the first thing that we need to do is draw the center of our circle. And the center of the circle occurs at the average stress. So our center, I'm going to denote that just as C, is going to be at sigma x plus sigma y divided by 2. That's the average in-plane stress. And so that's going to be the position along the normal stress axis, and there will be no component in the shear stress axis. So let's say that our center of our circle is right here then. And we'll denote that C. Next, what we'll do is draw our x face on. So we'll now plot the coordinates of our x face. So on our x face up here, I'll highlight this in red. On our x face we have normal stress sigma x and shear stress tau x y, and both of those are positive according to our sign convention. So we're going to go over a positive sigma x and then downward, since it's positive tau x y, and we'll say that this was the location of that point. So this is the point sigma x tau x y. Okay, and so that's a point on our circle. So we have a center, the center of our circle, and a point on our circle, which means we have our radius. And then you can sketch, since now we know the radius, you can sketch what the circle would look like. Okay, so I'm doing this by hand, so it's a little bit imperfect, but it'll generally look like this. So now this is very handy. We can define a lot of things on the Morse circle. So the first thing, we know that by our definition of principal stress, that's where we have our maximum normal stress or our minimum normal stress, and there's no component of shear stress. So our principal stresses will be right here, sigma 1. This is where we have our maximum stress, our maximum normal stress, while there's no component of shear stress, so there's 0 on the shear axis. This is sigma 2. So that's our minimum normal stress, no component of shear stress. And then remember that our maximum in-plane shear occurs when we're at the average value of our normal stresses. So our maximum shear will be the maximum value on the shear axis. So that's our max in-plane shear. it's the same value over here, just opposite sign, but same magnitude. So you can see from this, just by looking at this circle, we can now use trigonometry to calculate what our normal stresses are and what our max in-plane shear stresses are going to be. One thing to make sure that we keep in mind though is that when we've talked about stress transformations, when we're rotating by an angle theta with respect to the x-axis, those rotations correspond to a rotation of 2 theta on Mohr's circle. Okay, so we'll do a few calculations here just to make everything clear. Okay, so let's scoot this guy up a little bit. So if we wanted to know what our maximum stress is, sigma 1, we can see just by looking at the geometry that the maximum stress is equal to the center of the circle, and actually the minimum principal stress comes from the same method, but our maximum and minimum principal stresses, you can see, are simply the location of the center of the circle plus or minus the radius of the circle. Okay, so really what we need to do is figure out what the radius of the circle is. So we'll draw on our circle here to get the radius of the circle. Okay, so we're going to drop a right angle here. We know that this center is located at sigma x plus sigma y divided by 2. So that means that this distance right here is going to be equal to sigma x minus sigma x plus y divided by 2. Right? So it's the difference between this location's x-coordinate and this location's x-coordinate. So if we were to subtract those two, we're just going to end up with we'll end up with that distance being sigma x minus sigma y all over 2, and then this distance right here we can see is equal to tau x y, and then our radius is right here. So we can see our radius using Pythagorean's theorem is just sigma x minus sigma y over 2 squared plus tau x y squared. And we're taking the square root of that sum, so just by Pythagorean's theorem. And we know that the center of the circle is sigma x plus sigma y divided by 2. Okay, so right away we can see that our equation sigma 1, sigma 2 we derived visually is sigma x plus sigma y divided by 2 plus or minus this radical, which is sigma x minus sigma y over 2 squared plus tau x y squared. Okay? Now what if we want to know the angle at which the principal stresses occur? Right, so if we want to know what angle theta do we need to rotate do we need to transform the stresses? What angle theta do we rotate from our x-axis to the x prime axis where the principal stress occurs? Well, remember one rule is on the Mohr circle, an angle theta rotation of a stress element corresponds to a rotation of 2 theta on Mohr's circle. So if we need to go from this point to where the principal stress occurs, it's a rotation of theta p in reality, but on Morse circle we're going to rotate by 2 theta p. Okay, so that's the same angle right here. 2 theta p. Yeah, make that just a little neater. Two theta p. Oops, wrong color. Okay, so same thing. Now we can use trigonometry. We can see that the tangent of this angle is tau xy over sigma x minus sigma y over 2. And then this is a familiar equation for us. The tangent of that angle to tan 2 theta p, we just use definition of tangent. And that's going to be equal to tau xy over sigma x minus sigma y over 2. Okay, and that's the same equation for the principal angle that we'd used previously. Now let's talk about the max in-plane shear. Max in-plane shear, you can see, is just the radius. So max in-plane shear is equal to the radius. So we've written that equation for max in-plane shear right here. So max in-plane shear is equal to what the radius is equal to, which is sigma x minus sigma y divided by 2 squared plus tau xy squared. All of that, take the square root of it. Alright, what if we want to know the angle where the max shear stress is occurring? Well, we do the same thing. We can see that to go from this point, our coordinate that we originally plotted at sigma x tau xy, to go from that point on our x face to where does the tau max occur? Well, we're going to be rotating backwards now in the negative direction. Remember that counterclockwise is the positive direction for rotation, so we're going to rotate the other direction. So we need to rotate by 2 times theta s to calculate what is theta s. Since Morse circle, there's twice the rotation. And then from here we do trigonometry again. So we have another triangle here. We know that this angle is equal to 2 theta s. And our opposite side is sigma x minus sigma y over 2. Our adjacent side is tau xy. So the only thing that we really even need to pay attention to is the signs. So remember we said for this one we're rotating in the negative direction. So we have tan, we're rotating a negative 2 theta s. So that's the only reason we're calling that angle negative. In reality, and then tan of a negative angle is equal to negative tan of that angle. And then we had, for the tangent for our opposite side, we had sigma x minus sigma y over 2. Adjacent side was tau xy. And then if we just move the negative sign to the other side, so dividing both sides by -1, we have negative sigma x minus sigma y divided by 2 over tau xy. Alright, so that's right there is exactly the same as the equation that we had used previously. So here we can derive it geometrically. And what's great about this Mohr circle, you can use it for any stress transformation. It doesn't just have to be to find a principal stress or to find a max in-plane shear stress. So if you want to know and you can see very clearly that, so yeah, there's a few things we can note here. First, let's just make note that you can see that the angle of rotation to get between sigma 1 to right here. So the angle to sigma 1 and sigma 2 on Mohr circle, those are offset. Those are 180 degrees away from each other on the circle. So in reality, that means the angle, the principal angles are offset by half of that. In reality, they're offset by 90 degrees. Same with the maximum in-plane shear stress. Those are offset by 180 degrees, which means in reality they're offset by 180 degrees in Mohr circles. In reality, they're offset by 90 degrees. But we can go ahead and calculate any arbitrary rotation. If you want to have a stress transformation, you know, if we're starting at this point, you want to know, and if you want to calculate stresses at an orientation of any value for theta, then, you know, you can come to this point and rotate whatever value theta you're interested in. On Mohr circle, just rotate to theta, and then you can use trigonometry to figure out what is your coordinate on the normal stress axis and what is your coordinate on the shear stress axis. So this is a really convenient tool for doing any stress transformation.